Hello everyone, welcome back to the course on measurement and instrumentation, and today is the second lecture of our 8th week. We are discussing about temperature sensors here, and today we are going to talk about a new kind of transducer which is thermocouple for the temperature measurement. We have already seen two different kind of temperature sensors which are RTD and thermistors. In fact, we have also seen a semiconductor PN junction type of temperature detectors that we have seen that they are more useful, particularly when you want to integrate that over a microelectronics chip. Okay. So, today we will discuss the thermocouple, which is a very important class of temperature detectors, and the thermocouples is basically based on the thermoelectric phenomena which was discovered by Thomas Seebeck in 1821, and we will see that how this thermoelectric effect is essential for the thermocouples working. Okay. So, the electrically conductive materials exhibit basically three different type of thermoelectric phenomena. One is the Seebeck effect, and there are two more phenomena. One is Thomson effect and the Peltier effect. Okay. So, when any two metals are connected together, a voltage is developed which is a function of the temperature of the junction, and this is mainly the difference in the temperature, right. So, it was later found that the Seebeck voltage is sum of two different effects, the Peltier effect and the Thomson effect. The Peltier effect basically explains a voltage generated in a junction of two metal wires, while the Thomson effect explains a voltage generated by the temperature gradient in the wires. Okay. So, a thermoelectric contact transducer is known as thermocouple because at least you are requiring at least two different wires. So, two dissimilar or a couple of wires is required to form a junction. Okay. At least two of the junctions are needed to make a practical device. There are multiple type of thermocouples. We will see some of them. I have listed some of them here also, like we have a type T, type J, type K. These are base metal based thermocouple devices, while there are devices which are based on noble metals like type R or type S, type B. And if you see, all these different type of thermocouples are basically made up of two different metal pairs, okay, like or at least metal alloy pairs. Okay. If you see type T, it is basically a copper constant and junction, or two different wires are used, one is copper and another is the constant N. Okay. Type J require iron and constant N, then similarly K require the chromel and alumel, and type R and C, as I have earlier mentioned, require platinum and rhodium. Of course, both of them require platinum and rhodium, and there is a difference in percentage of rhodium in these cases. We will see, okay, later on in this course. Okay, but why I wanted to show you that if you see, every type of thermocouple require two metal pairs, right? Be it copper constant and be it iron constant and or so on. Okay, and based on the material used or based on the type of thermocouple device, you have their ranges. Okay, you can see that for type T, the range is like certain cryogenic temperature to 400 degrees Celsius or so. Similarly, other devices are also there. Type B can work even at 1800 degrees Celsius. Okay, so these are different ranges for the thermocouple devices. But what I wanted to highlight here is that they are all made up of a pair or a couple of wires, and that's why we are calling it thermocouples. Okay. Now, one of the most significant advantage of thermocouple is their extraordinary temperature span, unmatched by most of other temperature sensor, be it RTD or be it thermistor. Okay. So, it generates voltage in response to temperature and does not require any external excitation power. So, you can say that the thermocouples are basically self-powered temperature sensor. So, it is basically a direct converter of thermal energy into electrical energy. So, you are not providing any external bias or any external current. Okay. It is basically a voltage generating sensor. Sometimes thermocouple is that's why known as a thermal battery also. Okay. So practical exploitation of the Seebeck effect to measure temperature requires a combination of two wires with dissimilar Seebeck coefficient. Okay. Now since we know that what is a Seebeck effect, we are now talking in terms of Seebeck coefficient. Okay. I will let you know that what is basically a Seebeck coefficient is, okay, mathematically also, but please note here that we are talking about two different dissimilar materials now based on one parameter, that is the its Seebeck coefficient. Okay. Now the name thermocouple reflects the reality that wires with two different compositions are combined to form a thermocouple circuit. So you require two different wires of different materials, so heterogeneous kind of structure. Okay. Now consider this structure where I am taking a direction also. Okay. We'll take this direction later on. Okay, why the direction is important. Okay. Now I started from a junction TT and I am going to a junction TJ. Of course, this is I am going through a material A. Now I am coming back from the junction TJ to this junction. Okay, and this whole material is material B. Okay, and this is say TJ junction, and at this junction I have connected a voltmeter to measure the junction voltage or any voltage that is generated here. Okay. In this case, dE by dt is the rate of change of thermo EMF with respect to temperature, or if you see, we can call it thermoelectric power. Now this dE by dt is basically the Seebeck coefficient that we were talking in the previous slide. Okay. So if say I denote the Seebeck coefficient by sigma, which is of course a function of temperature, okay, I can write that sigma t is equal to dE by dt, or dE is equal to sigma into dt, where sigma is a function of temperature. Okay. Now the total EMF generated in material A between the junction at TT and TJ can be given as this EATJ. I am using this subscript A to denote material A. Okay. And then I am using this term T and J because this is between junction TT and junction TJ. Okay. Now if I integrate it, what I will get is sigma AT into dt TT to TJ. Okay. Now applying above equation to consecutive segment of the circuit, this will give you EAB as TT to TJ sigma A into dt, and then back from TJ to TT, okay, from this junction to this junction, okay, TJ to TT, and I am using the Seebeck coefficient for material B. Okay. So TJ to TT sigma B into dt. Okay. Now sigma A is the absolute Seebeck coefficient of material A, while sigma B is the absolute Seebeck coefficient of material B. Now the order of integration is specified by moving continuously around the loop from the terminal to the junction and back to the terminal. I am calling this terminal and I am calling this junction. Okay. So this is my junction and this is my terminal, because across this terminal I have connected the voltmeter. Okay. So the order of integration is specified by moving continuously around the loop from the terminal to the junction and back to the terminal, and the position of the junction around the thermocouple circuit is identified by the x coordinate, but you have to be very careful with the direction of x and the physical significance of the x. Okay. Now for the purpose of analyzing thermocouple circuits, the physical length of wire is actually doesn't matter much. Okay. So accordingly x should be thought of an indicator of the position only. So you should not be much worried about its position, where it is written or what kind of length the wire possess. Okay. So the wire length is in this case is immaterial, and x should be thought as indication of the position only and not a measure of distance. Okay. Notice that the value EAB in the last equation is due to integral along the length of the thermocouple element. Okay. Here the thermocouple junction is performing two different essential roles. One is the junction is providing electrical continuity between the two legs of the thermocouple. Let me call it positive leg and a negative leg. Okay. Now the junction also provides a heat conduction path that helps to maintain the end of the two dissimilar wires at the same temperature, which was the TJ. right? Now the EMF of the thermocouple exists because there is a temperature difference between the junction at Tj and the open circuit measurement temperature at terminal Tt. Okay, so switching the order of the limits of the second integral in that equation, it will help us in simplifying this. So what I want to say is just changing the order of this integration, say from Tt to Tj. Okay, now if you do that kind of changes here, what I am doing is I am just changing the order of limits. Okay, now this Tt is, say I am writing it here, and Tj I am writing it here, and say this is equation 1. So if you change this order, you will have to put a negative sign, right? So EAB is equal to Tt to Tj sigma A into dt minus Tt to Tj sigma B into dt, where sigma A and sigma B both are function of temperature. Okay, now what I can write is Tt to Tj integral of sigma A minus sigma B into dt. Now this defines the Seebeck coefficient of the material pair in place of material A and B. Now you can define sigma AB, and now sigma AB is defined as sigma A minus sigma B. Please note that similar to sigma A and sigma B, sigma AB is also a function of temperature. Okay, so if the two materials have the same absolute Seebeck coefficient, okay, means that sigma A and sigma B are 0, then the thermocouple actually will generate no EMF. So this equation will essentially become 0. All right. So regardless of the temperature difference Tj and Tt, and that's why I am emphasizing on the sentence or on the fact that when you are constructing the thermocouple, you should have a couple of wires which has different properties, at least in terms of the Seebeck coefficient. Okay, if you see, ideally you can generate EMF by any two materials or any two metals or their alloys. Okay, however, there are standard combination of materials that provide large value of sigma AB that are slowly varying with T, and that's why the names that you have seen, say type T, type B, type R, type S and so on. Okay, and it has evolved over the years. Okay, now substituting the definition of sigma AB in this equation, it will give you EAB or the EMF as Tt to Tj sigma AB into dt. Now this equation is the fundamental equation for the analysis of the thermocouple circuit, and I am calling this equation 2. Okay. However, this equation is also not in the form of computational formula for data reduction. Indeed, the conversion of thermocouple EMF to temperature does not require the evaluation of the integral also. Okay. So before a data reduction formula can be developed, let's dig out a role of the junction even in better sense. We have already seen two different roles of the junction. Okay. Now, since the thermoelectric EMF depends upon the difference in temperature between the hot junction and a reference junction, I am now not using a term cold junction. Cold junction means the junction where the temperature is less. I am not using that word now. I am calling it as a reference junction. Okay. So now I have two junction, hot junction and a reference junction. Now the temperature of the reference junction should remain absolutely constant in order that the calibration that I have initially will persist over the years, okay, of the operation of the thermocouple. Okay, and there are no errors on account of change in the ambient temperature. This can be also compensated by different electronics and so, but most of the time you want a very solid reference. Okay, the temperature of the reference junction is controlled for this purpose, and the reference junction temperature is usually kept at around 0 degree Celsius. The EMF produced in a thermocouple circuit now can be given in better form as E equal to A del theta plus B del theta square, plus you have more terms because the behavior of thermocouples are highly nonlinear. Okay, in this equation, this delta theta is basically the difference in the temperature between the hot thermocouple junction and the reference junction of the thermocouple, while A and B are constants. Okay, A is usually very large as compared with B. Therefore, the EMF of this thermocouple setup is equal to A into delta theta if you even ignore the values of B and other constants. Okay, so this difference del theta will be approximately equal to the EMF voltage divided by the constant A. Okay. Now there are three fundamental laws of thermocouples we should always remember. One is law of homogeneous materials. You will also find it as law of homogeneous conductors in some book. Okay. You have law of intermediate metals, and then we have third law as law of intermediate temperatures. So let's learn these laws, and this will help us in understanding that how different thermocouples has evolved over the years. So let's see first the law of homogeneous materials. It says that a single uniform conductor cannot produce an electromotive force merely due to temperature difference along its length. Okay, or we can also say that if both ends of a homogeneous metal conductor are subjected to different temperatures, no net voltage will be generated, regardless of the temperature distribution or the cross-sectional shapes of the conductor. Okay. So then second law is the law of intermediate metals or law of intermediate conductors. Okay. So it says that if a third metal conductor is introduced into the thermocouple circuit but maintains the same temperature at both its connection points, it will have actually no impact on the total EMF produced by the thermocouple. So actually the intermediate metal does not affect the measurement as long as it experiences no temperature gradient. So this is law of intermediate metals. Then the third law is law of intermediate temperatures. It states that the sum of the EMF developed by a thermocouple with say its junctions at a temperature T1 and T2, and then another junctions say T2 and T3 will be same as the EMF developed if the thermocouple junctions at temperature T1 and T3. Okay. So you have two junction temperatures T1 and T2, and then another is at T2 and T3, and this EMF will be same, or EMF developed will be same as the EMF developed if the thermocouple junctions are at temperature, initial temperatures at T1 and T3. This is known as law of intermediate temperature. Alright. So this is about different laws of thermocouples. Now let us see what are different kind of thermocouples that exist in the market, at least from the end point or from the point of end user. Okay. So thermocouples are basically classified under two major categories. One is the base metal thermocouples and another is the noble metal thermocouples. Base metal thermocouples are basically cost effective device based on different metal or their alloys, which are actually categorized as not noble metals. Okay. So that's why they are cost effective. So you have different base metal thermocouples, like you have type K, type J, type T, type E and type N kind of thermocouples, and based on the noble metals you have noble metal thermocouples. You have type R, type S and type B noble metal thermocouples. Okay. So let's talk about these different thermocouples in very brief. Okay. Let's learn from the base metal thermocouples and let's talk about say type K thermocouple. Okay. The type K thermocouple is basically the most widely used temperature sensor in industries. Okay. This is mainly because they have wide temperature range, they are durable and also cost effective, so they are very popular. Okay. And also most of these high temperature ambient are oxidizing atmosphere. So type K thermocouples are basically little bit resistance towards the highly oxidative environment. Okay. The material composition is very simple. You have positive leg as chromel and negative leg as alumel. Okay. Chromel is nothing but alloy of nickel and chromium, where you have nickel plus 10% of chromium, while negative leg has alumel, which is alloy of nickel, aluminum, manganese and silicon. Okay. Now The measurement range for type K thermocouple is usually from minus 200 degrees Celsius to around 1250 or 1260 degrees Celsius, while the optimal accuracy zone for this kind of device is from 0 degree to 1000 degrees Celsius, and usually it is not advisable for cryogenic temperatures. Okay, they have excellent balance between range and cost. Okay, so you have good mechanical toughness because you have seen that what kind of alloy is used for the fabrication. Okay, they have a strong resistance to oxidation, and that's why they are preferable for oxidative operations. Okay, they are suitable for continuous high temperature monitoring. And of course, like any other thermocouple, they are self driven or self powered thermocouple. Okay, then you have another thermocouple which is type J thermocouples. Okay, now the type J thermocouples is one of the oldest and most established temperature sensor that industry uses. Okay, so they are built from iron and constantan that I have earlier mentioned. It is particularly valued for high sensitivity and reliable performance at not very high temperature but in the moderate temperature range. Okay, and as I mentioned that it is made up of iron and the constantan. So positive leg is say made up of iron and the negative leg is made up of constantan, which is copper nickel alloy. Okay, the measurement range for this type J thermocouple is recommended around minus 40 degrees Celsius to 750 degrees Celsius, while the best accuracy zone is from 0 degrees Celsius to 600 degrees Celsius. But although if you see the range is or the span is smaller as compared to the type K devices, while the sensitivity of type J is better than type K instruments or type K thermocouples. Okay. Then you have another thermocouple which is type T thermocouples. The type T thermocouples is a highly stable and precise temperature sensor known for its excellent performance at low and even at sub-zero temperature. Okay, and they are constructed from copper and constantan. It is widely used in laboratories and even for cryogenic research. These type T thermocouples are preferred. In fact, food industry is also one of the area where this type T thermocouples has found its application. Okay, the material composition is also very simple. The positive leg is made up of copper, while negative leg is again made up of constantan, which is alloy of copper and nickel. All right, and the operate range is around minus 270 degrees Celsius to 400 degrees Celsius, and it provide you much better accuracy in the negative temperature region, and best accuracy zone for this kind of device is from minus 200 degrees Celsius to around 200 degrees Celsius, and that's why I mentioned initially also that they are best suited for the cryogenic application, at least for laboratory applications. Okay. Now, this type T thermocouples have excellent low temperature compatibility or capability. They have high measurement stability, strong resistance to even moisture, good signal strength and high signal to noise ratio, and they have long term repeatability. Okay. Then we have type E thermocouples. The type E thermocouple is known as the highest output voltage thermocouple among the commonly used base metal type thermocouples. The sensitivity is also pretty good. Because of its strong EMF generation and good stability, it is widely used in the precision measurement system, especially in the low to moderate temperature regime, and the material composition is again based on constantan and chromel. In fact, the positive leg is made up of chromel, which is the alloy of nickel and chromium, while negative leg is made up of constantan, which is alloy of copper and nickel, and typical range is from minus 270 degrees Celsius to 900 degrees Celsius, while best working range is again from minus 200 degrees Celsius to 600 degrees Celsius. All right. So, as I have earlier also mentioned and pointed out that type E thermocouples have highest thermoelectric output among base metals, and it has excellent signal to noise ratio and perform even very good in the sub-zero temperature range, and they have better accuracy than many alternative thermocouples, particularly in the low temperature regions. Okay. Then we have type N thermocouples in the base metal type thermocouples. The type N thermocouples was actually engineered as an advanced alternative to type K to overcome long-term stability problem at high temperature. Particularly, it has actually established in the modern days also as an alternative to type K devices because their range and all are very similar. Okay. It offers superior resistance to oxidation, it offers reduced drift and excellent metallurgical stability, making it ideal for critical industrial applications. Okay. The material composition is made up of nicrosyl and nicyl. The positive leg is nicrosyl, which is alloy of nickel, chromium and silicon, while negative leg is nicyl, which is nickel, silicon and magnesium. Okay. Operating temperature range is from minus 200 degrees Celsius to 1300 degrees Celsius, and short term capability can even cross 1300 and it can go to 1350 degrees Celsius or so. Okay. Then we have another class of thermocouples, which are the noble metal thermocouples, and mostly they are suitable for high temperature measurement. Let's see the first noble metal thermocouple, which is type R thermocouple. So the type R thermocouple is a noble metal temperature sensor designed for extremely high temperature and even with high accuracy applications. Unlike the base metal thermocouples, it uses platinum alloy that provide exceptional chemical stability and measurement precision. Please note that we have not introduced platinum till now. This is the first kind of thermocouple that we are studying having platinum component, and that's how it has been classified under noble metal thermocouple. Okay. The material composition is platinum plus 13% rhodium in the positive leg, while negative leg is pure platinum. Okay. And because both the elements are noble metal, the sensor resists any kind of oxidation, it also resists corrosion, and even they are very much immune towards any metallurgical aging. Okay. The operating range of type R thermocouples is in the range of 0 degree to 1600 degrees Celsius, and the primarily intended for extreme temperature environments where base metal thermocouples actually degrade very quickly. Okay. Then second thermocouple is type S thermocouple, and it is also very similar to type R, and this is basically preferred for high precision application where the role of temperature standardization and calibration plays a very important role. So kind of gold standard you can say. Okay. If you see, the positive leg is having 3% less rhodium, except that there is not much difference. So positive leg in case of type R thermocouple was platinum plus 13% rhodium. Here you have platinum plus only 10% of rhodium, while negative leg is again made up of pure platinum, very similar to type R. Okay. However, the ranges and all are also very similar. So recommended range is also from 0 to 1600 degrees Celsius. Okay. Then we have type B thermocouples. The type B thermocouples is designed for ultra high temperature measurement, and unlike the common thermocouples that degrade above 1200 degrees Celsius, type B can operate continuously up to 1700 degrees Celsius and even can tolerate short bursts of around 1800 degrees Celsius, and that's why wherever you will read, you will find that the range of type B thermocouples are up to 1800 degrees Celsius, and material composition is again very similar to type R and type S, except that the positive leg has now much higher concentration of rhodium, which is now platinum plus 30% rhodium, while in the negative leg till now for type R and type S we have only seen that pure platinum is used, while here you have around 6% of rhodium also. So you have platinum plus 30% of rhodium in positive leg, while you have platinum plus 6% of rhodium in the negative leg. Okay. So the high rhodium content in the positive leg increases the melting temperature and the creep resistance of the leg. Okay. And it produces stable thermoelectric output at even extremely high temperature, and it maintains the grain structure longer, preventing any calibration drift, while the higher concentration or say 6% introduction of rhodium in case of negative leg actually keep the alloy ductile and easier to fabricate. It also provides the required electrical contrast with the positive leg where you have 30% of rhodium, and it improves the long-term reproducibility of the voltage output. Okay. So the 24% rhodium difference is carefully chosen and it's not a random thought. Okay. So this 24% of rhodium difference is actually large enough to generate the usable EMF, while this is small enough to maintain the metallurgical compatibility between the two legs at even extremely high temperature. Okay. So this is a little bit about different thermocouples that already exist in the market. Okay, the advantage of the thermocouples over the thermistors and RTDs, I hope that you must have understood till now. Okay, the thermocouple, you have already seen that type B can go up to 1800 degrees Celsius. I'm talking about the upper limit, while the RTD and thermistors can go around say 600 to 850 degrees Celsius and till 300 degrees Celsius respectively. So when you require very high temperature, you will of course look for the thermocouples. And another advantage that you must have noticed is that the thermocouples are self-powered. So thermocouple operates using the Seebeck effect, which generates voltage directly from the temperature difference. So no excitation current means that there is no self-heating error. Okay, and it can also work during the power failure, and you can use it for the remote sensing. Say if you want to monitor say temperature of a blast furnace or that kind of high temperature, for those applications you can use it for the remote applications. Okay, they also have very good mechanical strength because most of them are made up of strong alloys. Okay, so they are resistant to any kind of shock, vibration, high pressure, or even the corrosive atmospheres. Okay. Now the disadvantage of the thermocouples over the existing thermistors and RTDs are like a thermistor does not measure absolute temperature. Okay, so it measures basically the temperature difference between the measuring junction and the reference junction. Okay, since you are measuring a temperature difference in place of direct temperature, okay, you must have electronics or circuitry to compensate for any variation in the ambient temperature. Okay, and a poor cold junction compensation calibration in case of these thermocouples will lead to systematic error. Okay, and rapid ambient changes will definitely lead to the measurement drift, and these things has to be compensated. Okay, then there are other disadvantages, like when you talk about temperature of the order of say 1500 1600 degrees Celsius, at that high temperatures metal can undergo oxidation, and there can be subsequent grain growth and contamination can be there, and some particles may diffuse in the metal at this kind of high temperature, means that you will see there is a voltage temperature relationship changing maybe very slowly, and this means that your calibration is getting directly affected. Okay, so for this kind of thing, you will see that thermistors and RTDs are still relevant, and it's not that every function has to be done only by the thermocouples. We have to, or the end user has to be very clever while choosing these kind of temperature sensor for their intended applications. Okay, so with this we have finished our discussion on temperature detection. In our next class, we will be discussing some other kind of transducers. We will continue our discussion on the transducers in the next class also. Thank you.